Audio Jungle.
Torque is a measure of the force that can cause an object to rotate about an axis. Force is what causes an object to accelerate in linear kinematics. Similarly, torque is what causes an angular acceleration. Hence, torque can be defined as the rotational equivalent of linear force. The point when the object rotates is called the axis of rotation. In physics, torque is simply the tendency of a force to turn or twist. There's different types of torques. Torque can either be static or dynamic. Static torque is a torque that does not produce an angular acceleration. A person pushing a closed door, pedaling a cycle at a constant speed is also an example of a static torque, as there is no acceleration. An object is in rotational equilibrium if the velocity of its rotation is constant. An object that is not rotating or an object that is rotating in one direction at constant rate will be considered in rotational equilibrium. To be in rotational equilibrium, the net torque acting on the object must be zero.
Gravity, also called gravitation in mechanics, the universal force of attraction acting between all matters, is by far the weakest known force in nature and thus plays no role in determining the internal properties of everyday matter. On the other hand, through its long reach and universal action, it controls the trajectories of bodies in the solar system and elsewhere in the universe and the structures of evolution of stars, galaxies, and the whole cosmos. On Earth, all bodies have a weight or downward force of gravity proportional to their mass, which Earth's mass exerts on them. Gravity is measured by the acceleration that it gives to freely falling objects. At Earth's surface, the acceleration of gravity is about 9.8 meters, 32 feet per second. Thus, for every second an object is in free fall, its speed increases by about 9.8 meters per second. At the surface of the moon, the acceleration of freely falling body is about 1.6 meters per second. Mass depends on how much matter, atoms, and so on there is in an object. More mass means more inertia, as there is more to get moving. This is Isaac Newton's idea of mass, which underpins his famous law of motion developed in the late 16th. It is not quite accurate at extremely high speeds, where Albert Einstein's 20th century theory of special relativity is required, but it's fine for most everyday situations. Weight, on the other hand, is a measure of the amount of downward force that gravity exerts on an object. This force increases with the object's mass. The more inertia it has, the harder gravity pulls. On Earth's surface, the force of gravity is about 9.8 newtons per kilogram. To hold up our pulley, we used a wooden base and that connected a piece of wood. It went up to the top, and at the top point we had our pulley. We used 3 weights to carry out our experiment, one of 50 grams, the other 100 grams, and the third one 200 grams. For our axis, we used a wooden table with marks to be able to locate the weights. It is balanced on a wooden base with a triangular shape. For our first experiment, we put the upward force with a 50-gram weight on the 30 centimeter mark on the right side. $200-gram weight was put on the 17.5 centimeter mark on the right side. The 100-gram weight was put on the 10 centimeter mark on the left side. For the first experiment, to be able to solve it, we first converted our kilograms of our weights into newtons. For the first one, we multiply 0.1 kilogram times 9.81 meters per second squared, which gave us 0.981 newtons. For the second one, we multiplied 0.2 kilograms times 9.81 meters per second squared. That gave us 1.962 newtons. And for the last and third, we multiplied our 0.05 kilograms times 9.81 meters per second squared, which gave us 4,905 newtons. Now, to continue with our experiment, we have to remember that the summatory of all the torques that are given in the system is equal to 0. So now, knowing that the first torque is going anti-clockwise, we know now that it's positive. So now we multiply the distance between the weight and the base, which is 0.3 meters, times the value of the weight, which is 4,905 newtons, and add the result of 0.2 meters times 9.81 newtons, which is 34.335 newton meters. So since at the end of this equation we subtract the other weight, which is 1.962 newtons, we now have an equation that is 34.335 newton meters equal to that weight, which is 1.962 newtons. So now, having this, we divide 34.335 divided by 1.962 newtons, which is equal to 0.175 meters. And this is the distance between the base and the second weight to give equilibrium to the system. For the second experiment, once again we put the 50-gram weight on the upward force on our pulley, and the 200-gram weight 5 centimeters from in between the base and our marker on our axis. So to find the other mark to put our other weight of 100 grams, we did our equations and got a result of 0.25 meters, which is 25 centimeters. So the 100-gram weight, we put it on our 25 centimeter mark on our axis, giving us a result and equilibrium.
For the second experiment, we used 3 different weights given in mass. The first one was 50 grams, the second one was 100 grams, and the third one was 200 grams, in a bar of length of 60 centimeters or 0.6 meters. In order to obtain the equation, what we must do first is we have to change that value in mass into a value of weight, which is the newtons. So what we had to do, we have to multiply that value in mass times the gravity, which is 9.81 meters per second per second. So, for example, we multiply the first mass, 50 grams, times 9.81 meters per second, but we have to change the value of grams into an equivalent in kilograms. So we multiply 0.05 kilograms times 9.81 meters per second, and the result is 0.4905 newtons. That's the first weight. The second weight is given by 0.1 kilograms, which is the equivalent of 100 grams, times 9.81 meters per second, and the result is 0.981 newtons, which is the second weight. And for the last weight, the third one, we multiply the equivalent of 200 grams into kilograms, which is 0.2 kilograms, times 9.81 meters per second, and the result is 1.962 newtons, and that's the third weight. Now, we have to remember that the summatory of all the torques given in the system is gonna be 0. So we have to first find those torques individually, then add them all together, and the result has to be 0. So, for example, for the first torque, since we know that if the torque goes clockwise is gonna be negative, or it goes anti-clockwise is going to be positive. We know that the first torque it has to be negative since it's going clockwise. So we multiply the distance between the weight and the base, which is 0.3 meters, times the value of the weight, which is 0.4905 newtons. And then we add the result of the other multiplication, which is the distance of the base to the third weight, which is 5 centimeters, and the equivalent is 0.05 meters, times the value of the third weight, which is 1.962 newtons. The summatory of those two values is going to be 0.24525 newtons meter. And now that result is going to be times the distance of the second weight of the 100 grams times 0.981 newtons. So what we have to do is we have to divide the result that we got from the summatory of the other two values. We have to divide that for 0.981 newtons, since it's the value that it's multiplying the distance between the base and the second weight that we don't know that distance. So we do that division and the result is going to be 0.25 meters, and that is going to be the distance between the base and the second weight, which is 100 grams or 0.1 kilograms, in order to obtain equilibrium in this system.